welcome to section 5.1, distance and accumulated change. So the last few chapters we've been learning about derivatives, specifically talking about rate. In this chapter and our chapters moving forward, we are going to be talking about integrals. They are related to the derivative, okay, but this time, as you can see in our very first example, we're already given a rate. So we are handed a derivative to us. Alright, and we're going to do some other calculations with it. So, in our first example, suppose a car is moving with increasing velocity, that's our rate, and we measure the car's velocity every 2 seconds, obtaining the data in this table. We want to know how far has the car traveled. So now we know how long the car has been traveling, the time, and we know how fast the car has been traveling, but we would like to know how far, so the distance. Alright, so we can't calculate this exactly because we only have the time and the speed measured every 2 seconds. Alright, so we don't know how fast the car is going at every single moment. So we can only estimate, there we go, estimate the total distance because we do not have measurements for every moment in time. We would have to know how fast the car was going for every single moment in order to calculate this exactly. However, we can do an estimation. So first, let's recall a formula, okay? If we remember, that relates distance to rate and time. So our distance is equal to rate times time. Alright, in this case our rate is our velocity. Alright, so rate is velocity here. So we can calculate our total distance over these 6 seconds, alright, by multiplying the velocity and the time respectively. Okay, so let's see, in between seconds 0 and 2, the car is going somewhere between 20 feet per second and 30 feet per second. Do you agree with that statement? Think about it for a second. At 0 seconds, it's going it's going exactly 20 miles an hour, or 20 feet per second, sorry. And at 2 seconds, it's going exactly 30 feet per second. So in between 0 and 2 seconds, it's got to be in between 20 and 30 feet per second, right? So we're going to do an underestimate, okay, because we're going to think the car is going at least some speed, okay? So if we are doing an underestimate, we know the slowest that the car could possibly go. So I'll bring this down here. So the slowest the car could go between 0 and 2 is 20 feet per second. Alright? So if we're going to say it's going at least 20 feet per second, we're going to say, okay, 20 feet per second times the amount of time that has lapsed between 0 and 2, which is 2 seconds. Okay? So that's going to give us a rough estimate of the distance traveled in the first 2 seconds. But what about the rest of it? We need to add it all together, right? So we need to add this to the slowest the car could be going between 2 and 4. Alright, which is going to be 30 feet per second. Again, multiplied by the amount of time that has lapsed between 2 and 4, which is, again, 2 seconds, right? So our time intervals are remaining the same. Okay. So again, we need to add this to the slowest the car could be going between 4 and 6, which is 38. Again, times 2. So if we add all this up, we get that our total distance is 176 feet. Alright. This is an underestimate, again, because we said the car was going at least some speed. Now let's switch it around and let's do an overestimate. Alright, so now we want to think the car is going at most what speed in a certain time interval. Okay? So, that graph came up way too soon. We'll look at that in a little bit. Alright, we need our overestimate. So, our total distance is, well, how fast, the fastest the car could be going between 0 and 2 is somewhere between 20 and 30 feet per second, so we're going to pick the larger number. So we're going to pick 30 feet per second. But we're still looking at the same time interval, so it's still times 2 seconds. Okay? Then again, between seconds 2 and 4, we're going to pick 38. Okay? And between seconds 4 and 6, we're going to pick 44 feet per second. Also still times 2. And if we add all this up together, we get 224 feet. That's a difference of 48 feet. So we have an underestimate and an overestimate that disagree by 48 feet, which is pretty significant if you think about it. But at least we know, so now we know that the car traveled at least 176 feet and at most 224 feet. If we wanted to make a better estimate, we could actually take the average of the two. So a better estimate would be 176 plus 224 divided by 2, which gives us 200 feet. Alright, so if we meet in the middle, we actually get a better estimate. So the middle between our over and under estimates. Alright, so now I want to look at that graph. I want that graph to come back up. There it is. Alright, let's make it a little bigger. Alright, so this is a graph of all of our data points. Alright, so we have the horizontal axis is our time in seconds, and our vertical axis is our rate. Okay? And so this is a graph of the velocity function. Alright, and you can see here that I've labeled all of our time intervals of 2 seconds. So, what we were doing, if we think about it, let's look at the first time interval between 0 and 2. Alright, if this value here is length 2, which we know that to be true between 0 and 2, as a length of 2, and the data point associated with what we chose was 20. Remember, if we did this 20 times 2 for our underestimate. All right, let's go up to 20. If we multiply 20 times 2, what do we get? If you think geometrically, think of shapes. Does this give us the area of a rectangle? If I could spell rectangle? Well, let's go ahead and draw the rest of our rectangle. There you go. 2 times 20 gives us the area of a rectangle. All right, let's look at our second data point. We know again we have the same length on our bottom, so we have the length 2, but this time for our underestimate, we chose to look at 30. Not drawing these perfectly, let's see. Here we go, it's a little better. Our next interval, now we have this rectangle, so we have 2 times 20, and that's our last rectangle. So our total area is going to be the sum of all 3 areas, which is exactly how we just calculated the distance. But remember, this was our underestimate. How about our overestimate? How did that one look? Alright, so instead of completely making this graph crazy, I'm actually going to copy and paste it over here. Maybe. There we go. Okay. Get rid of all of this. Alright, our intervals are going to remain the same, but I'll go ahead and draw them in a different color. Alright, my color needs to be bigger. There we go. There we go. Alright, and so let's think of how we calculated our overestimate a moment ago. We picked the higher possible value when looking at our rate. So for the first 2 seconds, this area is going to be 2 times 30. For our second rectangle, it's still 2, but we picked 38 as our height. So we're going to come over here and attempt to connect them in a typical manner. There we go. For our third rectangle, we picked 44 as our height. Alright, so this is area 3, and it's 2 times 44. And we did the same thing where our total area is going to be the sum of all 3 areas. Okay. Now let's go ahead and zoom out so we can see both of these. What both of these are doing is approximating the area under that curve. All right, so under our function, v of t, under this line, I'll say it under this curve, we are approximating the whole area underneath of here. All right? So, can we tell why it's an underestimate and why it's an overestimate? Well, let's look at this underestimate. We're missing all of this. All right, so we're missing all of this area. That's why we get an underestimate here. And for an overestimate, we're counting extra area that's not under the curve. So now we are counting too much area. So that's how we get an overestimate. Okay, so what we did here was we calculated the areas of rectangles and tried to estimate the area under a smooth function where it's not a bunch of steps, if you will. So this is not a perfect calculation, it's an estimate, right? And we noticed that we were pretty far off. Our overestimate and our underestimate were pretty far from each other. If we averaged them, it minimized that error a little bit. Okay? How do you think, take a minute, think about this, how do you think we could make an overestimate or an underestimate better? How could we make a few rectangles look more like a curve? Okay? So we are going to see proof of this in just a second, but what if we added more rectangles? Okay, so I'm going to go ahead and, yep, there we go, paste that again. Okay, and say, well, what if we split this in half? And we split this one in half. And we split this one in half. Looks like there's less area that we're missing there from the underestimate, right? So we're just going to make a little note that adding more rectangles would make a better approximation. All right, it's essentially getting less and less pixelated if you think about it that way. All right, so now we're going to jump into example 2 and show you numerically how this makes a better approximation. All right, so if t is in hours since the start of a 20-hour period, a bacteria population increases at a rate given by f of t is equal to 3 plus 0.1 t squared, millions of bacteria per hour. We are supposed to calculate the left-hand sum to estimate the total change in the number of bacteria over the 24-hour period, using intervals of length 4. Okay, so this left-hand sum, explain this for a moment. If we remember just our graph a moment ago, sum of the values, we did a box that came underneath, and this is where we counted the left value as the height, the left value. Okay, so this would be our left-hand sum. And again, if we calculated our point here, and again as our top point here, this would be our right value. So this would have been a right-hand sum. Okay? So we want to go ahead and calculate the left-hand sum. And I'm going to actually define these more in depth in a moment. Okay? So calculate the left-hand sum to estimate the total change in the number of bacteria over the 20-hour period using intervals of length 4. So if t is in hours, all right, that means our length is 4 hours. Okay? This is the size of our intervals. In our first example, we were looking at intervals of length 2. Okay, here we're looking at intervals of length 4. So how many intervals do we need? Alright, in this case also, this is delta t, the change in t, right? So the number of intervals, which we just call n, is the total amount of time. So we have a 20-hour period, so it's the total amount of time divided by the length of the interval. So the length of the interval is 4. Okay. And so we have 20 divided by 4, which is 5. So this is going to be 5 intervals. Alright, so let's go ahead and set up a table here. So we have our t values, and then we have our rate values. Okay? So our t values start at 0. Okay? And they're going to increase by 4. So we have 0 to 4, to 8, to 12, to 16, and they go up to 20 hours. Okay? And now we need to calculate the rate at each t value. So this is r of t, and remember, r was given to us as f of t is equal to 3 plus 0.1 t squared. Alright, so this is the formula I'm using to just go ahead and fill in these values down here. Alright, so our rate at each point, 17.4, 28.6, and 43.0. Alright, so let's go ahead and take an underestimate first. Alright, so an underestimate. Well, if we take a look at our values, we recognize that all of the rates are increasing. So if again we're picking the left-hand sum, this would be our underestimate because we'd be picking the lower values each time. Alright, so an underestimate is the left-hand sum in this case. I'll make a note that this is not all of the time, alright, but in this case. So we need our total growth. Well, that's going to be equal to our time interval, which is 4. The length of our interval is 4 times the slowest growth rate possible in the first 4 seconds, which is 3. Alright, so 4 times 3. But then we need to add that to the interval again, times the slowest possible growth rate in between 4 and 8. So we pick 4.6. 4.6. Okay, then again we need 4 times 9.4. And 4 times 17.4. Add that to 4 times 28.6. Alright, so let's make sure we get 1, 2, 3, 4, 5 intervals. Okay? We add this all together and we get 252 million bacteria. Okay? So our total growth that happened in 24 hours, we think, has to be at least 252 million bacteria. And that was measuring every 4 hours. So remember what I talked about when I said maybe adding more rectangles. So that means adding more measurements would make a better approximation. So part B is going to let us give that a try. We're going to calculate the same thing, but using a length of 2. Alright, so here our delta t is equal to 2. That means our number of intervals is 20 divided by 2, so we have 10 intervals. So our table is going to go 0, 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20. Okay? And our rate values, we have 3, 3.4, 4.6, 6.6, 9.4, 13, 17.4, 22.6, 28.6, 35.4, and 43. Alright, I know that's kind of a messy table, but there we have it. So, and again we used the function given to calculate those rate values. Okay, so now our total growth well, now we have to go through and do the left-hand sum of all of these intervals. Alright, so here our interval length is only 2. So we do 2 times the lowest rate in between the first two, which is 3. Alright, plus 2 times the lowest rate in between the second two, which is 3.4. Alright, plus 2 times 4.6. And in interest of time, I'm not going to write this all out, but our last one would be 2 times 28.6. And we'd end up with 288 million bacteria. Alright, so our first estimate gave us 252 million. Our second estimate gave us 288 million. So part C tells us that the true growth value is 326.7 million. Alright, so neither one of our estimates were great, but which one was better? Which one was the closest? 252 or 288? And the answer is the second approximation, with delta t is equal to 2. So maybe if you want, try it again with delta t equals to 1 and see, can you get even closer to that 326.7 million number? Alright, so now what we just learned was the basis of what is called Riemann sums. Okay, and we're not going to go too in-depth into this, but we're now going to write down the formulas that we've been using without even knowing it. Okay, so say we've been given an interval. So an interval from A to B. Okay, and we have some delta t value or some n value. We can always find one from the other using n is equal to b minus a over delta t. And similarly, we have delta t is equal to b minus a over n. Okay? So again, if we're looking on a graph, and we have some function here, this t sub 0, this is our a value, and this t sub n, okay, this is our b value. So the length of our interval is b minus a, right? Okay, so the formulas that we've been using, let's look at the right-hand sum. Well, we use what's called summation notation, so we get this little zigzag going on, okay? And we're going to start at I is equal to 1 and go up to n rectangles, okay? And so then we have the function value at the t value, okay, and then we're going to multiply this by the length of our intervals. So what this looks like, if we expand it out a little bit, this would be our function value at t sub I, but I starts at 1, so sub 1 times delta t. Then the big zigzag means a sum. We are adding. So we add that to f of t sub 2 times delta t. Okay? This is exactly what we were already doing. This is just the formal definition for it, okay? And you'd keep going all the way until you reached the last t value, t sub n. Again, times the length of the interval. Alright, then we have the left-hand sum, which is very similar. The only difference is now we're starting at I is equal to 0, okay, and we're going up to n minus 1. So we have but everything else is the same, so it's still function value at t sub I times the length of the interval, but this time in our right-hand sum we started at f of t sub 1. This time in our left-hand sum we're starting at f of t sub 0 times delta t. Then we get to f of t sub 1 times delta t. And we keep going, but we stop one sooner. So we stop at f of t of n minus 1 times delta t. Okay. So now I'm going to make a quick note about upper and lower estimates. So upper and lower estimates versus left and right sums. All right, they're not always the same. In all of the cases that we've seen today, the left-hand sum was the underestimate. Okay, so let's take a look. Today we looked at multiple graphs that were concave down. Right? So if this is concave down, we're going to pick the left estimates. All right. So this is a left-hand sum. And in this case, this is an under or a lower estimate. However, if we look at a graph that is our left-hand estimates, so this is a left-hand sum, and in this case it's going to be an over or an upper estimate. And similar with the right-hand sums, all right? So it's just very important to notice that upper doesn't immediately correlate with the right-hand sum, and likewise for lower and left. All right, so it's important to look at the function that you're dealing with on a graph to actually know which one's going to be the lower and which one's going to be the upper approximations. All right, we're going to do one more example. Example 3. So we have the velocity of a car in feet per second is 10 times t. Okay, and t is going from 0 to 6. We want to use intervals of length 2 to give upper and lower estimates for the distance traveled. Okay, so we're going to go ahead and calculate both the left-hand and the right-hand sums. We might not know exactly which one is the upper and lower yet, but we'll find out. Okay, so length, our delta t, so we need to find the number of intervals. So if we want to go ahead and set up our table, and 60. Okay, so I'm going to go ahead and use our formal definition here. So and going up to n minus 1, so n is 3, 2. Delta t. I write all of this out. And that's 3 calculations, so those are our 3 intervals. All right, v of t sub 0, well that would be v of 0 plus plus v of 4 times 2. V of 4 is, so we get 40 plus 80 gives 20. Okay. Then if we want, okay, but now instead of starting at t, and we end with v of t sub 3. Those are the 3 intervals. Alright, the left-hand sum gave us 120, and the right-hand sum gave us 240. Alright, so now we want to know what is the average. So that's the left hand, that's the right hand. So the average is going to be 120 plus 240 divided by 2. So we get 380 divided by 2, 190. Alright, so this is our average. So that wraps up the start of Chapter 5. Please let me know if you have any questions. I'm happy to answer them. And don't forget to take the comprehension quiz.